Hi, I'm Nathan. I'm a PhD candidate in the Shinoy Group in the Material Science and Engineering Department at the University of Pennsylvania. And my talk for the 2020 MRS Spring and Fall meeting is titled Machine Learning Enabled Design of Point Defects in 2D Materials. The big question that I want to answer is, how do we engineer defect states that are electrically, magnetically, and optically addressable in solid-state devices? I'm going to focus specifically on 2D or layered materials because the electronic, magnetic, and topological properties in these systems are very tunable. We can think of them as really the whole material is a surface, so it's very accessible. We can think about devices made out of these materials that are low power, obviously very compact because of the 2D nature, and also flexible with interesting mechanical properties. We can stack them together into designer heterostructures or superlattices and really integrate these materials into solid-state devices. I'm also going to focus on two specific exciting applications of point defects in 2D materials. The first is atomically thin resistive memory devices, or atom ristors, where a 2D material is sandwiched between two metal electrodes, and defect states are reversible and can be used as a kind of a brain-like or neuromorphic memory. The second application is quantum emission, where defect states can be controlled to emit single photons of light. To get started, we need to be able to identify host materials with properties that make them useful and usable for these defect technologies. So to predict those properties, we use something called deep transfer learning, where starting with a deep neural network that is trained on 10,000 or even 100,000 bulk 3D crystals, the model is able to learn something about the physics and structure that allows us to predict properties. Then we can take those trained models and fine-tune them on the much smaller amount of available 2D materials that we know about, something on the order of maybe 1,000. We take theoretical and experimentally known 2D materials and represent them as graphs, where nodes are atoms and edges are bonds. And then that trained deep learning model is able to predict key quantities about the host materials quite well. So we can see here, for example, computing the thermodynamic formation energy of 2D materials. It does very well. After identifying around 150 host 2D materials that might be useful and interesting for the applications we have in mind, so we can identify those materials either by looking up things like their band gap and stability in a database, or by predicting them using our deep neural networks. We take those host materials and for each one, construct around 70 different defect structures based on things like vacancies, die vacancies, and all sorts of substitutions. So we generate around 10,000 theoretical defect structures. For around 1,000 of those, we compute full band structures for those defects. And really our goal is to quickly identify the ones that are most interesting for our applications and that are engineerable. So we want to create machine learning models that allow us to bypass these very expensive, time-consuming first principles calculations to narrow down our search. For that, we identify two particular targets that are kind of first-order filters, things we need to know about potential defects to see whether we should evaluate them further. The first target is really just the binding energy or the formation energy that it costs to create that defect. And then the second target is the defect level position. So the energy level that is associated with that defect, we want to know whether it sits in the band gap and is potentially accessible and controllable, or whether it sits very close to the bulk band edges or even resonant with the band edges, and so therefore is not accessible. Here we're showing the first target again. This is just a plot of the defect formation energies for those 1,000 defects that we ran first principles calculations for. And then the second target, which is showing we're really going to try to quantify whether a defect's energy level is a deep defect, so more than kT away from the bulk bands and energy at room temperature, or a shallow defect where it is less than kT away from the bulk bands. For the machine learning models, to predict these targets, there's a really important thing to note is that we don't want to use any inputs from calculations. So we're going to parameterize the host materials with properties that we can either look up from a database or easily predict with our deep neural nets. And then the defect properties are things that we can really just look up from the periodic table. So say, for instance, I have a tin atom sitting in a lattice and I substitute in a selenium atom, then that defect is going to be parameterized by how the atom has changed. So changes in the atomic radius, in the electronegativity, things like that. So with these inputs about the host and the defect and no inputs from calculations, we're able to train random forest machine learning models that are able to predict these two target quantities. Some of the particular properties are listed here in rank from their importance, and they really fall into two categories. The first are strain terms that correspond to the bonds in the lattice spontaneously relaxing due to the defect of trying to lower the energy. And then the second category is really all the messy electrostatic interactions, charge transfer, things like that. Using these features in the model, we're able to get pretty good performance predicting the defect formation energy, at least good enough to sort of quantify whether a defect is likely to form or really not likely at all to form. And then we're able to do very well determining whether a defect will end up being a shallow or a deep level. We define this concept of a defect score that really encodes a lot of different properties that we know are needed for quantum emission. Then we rank our predicted or proposed defects by that score. That allows us to identify some pretty interesting candidates across new material systems that have not been considered in experiments. We do a similar kind of ranking for the non-volatile resistive memory devices, looking at defects in particular based on their binding energy, where we have identified defects that are very stable and others that have a really low switching voltage. So both potentially interesting for different neuromorphic type technologies. So these scores have allowed us to kind of quickly identify and propose over 100 interesting defects for quantum emission and 15 unique candidates for the atomically thin memristor application. To summarize, the first key takeaway is we've shown point defects in 2D materials are a viable platform for quantum information science and non-volatile memory. In particular, we showed that machine learning is an interesting tool to accelerate the identification of lots of promising candidates for these applications. And then second, we showed some specific material systems, including various layered metal chalcogenides, hexagonal nitrides, and metal halides that have interesting defect structures to investigate and that are at least currently totally unexplored. This work was recently published in ACS Nano, so I'd encourage you to check out the paper for all of the details, and also you can follow this link here to my Google Scholar with all of my publications. Thank you very much for listening. Thanks to my collaborators Deep Jarawala at Penn and Deji Akinwande at the University of Texas at Austin. And my contact info is on the left side of this slide. Feel free to reach out to me on any of those platforms if you have any questions about this work or would like to chat about anything.